right, ladies and gentlemen, welcome to the mole conversions review. Just going over some sample problems that, again, you've probably seen similar things in Regents Chemistry, just getting them back into your head for AP Chemistry. So a little bit of a review, what do I mean by mole conversions? Essentially, I'm referring to the mole map from Regents Chemistry, the really basic stuff of how the mole allows you to convert several units back and forth to one another. And the units that we're going to focus on are grams, particles, and volume, units, the measurements, I should say. Uh, we can convert grams to moles using the gram formula mass of a compound or an element. And this right here is really the big one that we're going to be using all the time throughout the entire year in AP Chemistry. That grams to moles using GFM. Now it might not be called GFM, it might be called formula weight, it might be called formula mass, it might be called atomic mass or atomic weight. It means the same thing, this concept of adding up the individual masses of all the elements until we get the gram formula mass. It's grams per mole. That's the unit for GFM. So we can convert grams to moles using GFM. Particles, you can do atoms, you can do molecules, you can do formula units, which is what we call it if it's an ionic compound. This is through Avogadro's number, 6.02 times 10 to the 23rd particles equals 1 mole. Now it could be, atoms equal 6.02 times 10 to the 23rd atoms equals 1 mole. Molecules, that number of molecules equals 1 mole. This will come up less often, realistically. It's grams to moles, that's really the big one. And then the final one, volume to moles. The thing that I want to, again, emphasize about this one, this is not volume of anything. It is a very particular type of volume. It has to be a gas, it has to be at STP, and it is only for liters. So 22.4 liters of a gas at STP is equal to 1 mole of that gas. If we are not at STP, we cannot use this. If we do not have a gas, we cannot use this. Students tend to use this for things like solutions. I say you've got 2 liters of sodium chloride. How many moles of sodium chloride do you have in there? You cannot use this there. This is only for gas at STP. So going through a couple sample problems, we're going to do this with dimensional analysis. First up, how many molecules are in 50.3 grams of sulfur dioxide? You need to get it into your head that as soon as you see mass, 50.3 grams, what are you going to do with it? You are going to immediately turn this thing into moles. It is a gut check reaction for you. I want that in this class. As soon as you see the mass of one compound, the first thing you should think would be let's turn it into moles. Mass to moles. How do we do that? We do that using gram formula mass. Okay, gram formula mass of what? Sulfur dioxide. See how Mrs. Julian is a little tricky here? I don't give you the formula. So, sulfur dioxide. Well, it's a molecular compound, meaning it's got covalent bonds, 2 elements, both nonmetals, sulfur and oxygen. Prefixes tell you what's what. So sulfur dioxide, that's really easy. That's SO2. So we're going to start with the number the problem gives us, 50.3 grams of SO2. And I'll do this with T-charts. Sure, why not? Set up the first T-chart, take the unit, drop it down, grams. Well, what grams? GFM, so we need the GFM of sulfur dioxide. GFM of sulfur dioxide, okay, sulfur is 32.1, oxygen is 16, and there are 2 of them, so we get a gram formula mass of 64.1 grams. Every 64.1 grams is 1 mole of sulfur dioxide. This right here is your GFM, grams per 1 mole. But we don't want moles. The problem asked about molecules. Notice how I didn't even care initially what it was asking for. I just saw grams and immediately converted it to moles. That's what you're going to be doing. You see grams, you automatically convert it into moles, like 99% of the time. That's what we're going to be doing in here. Okay, so we've gotten rid of grams of sulfur dioxide. Right now we have moles of sulfur dioxide, but we don't want that. We want molecules. So the conversion for molecules is now for every 1 mole of something. Again, see how I'm taking that unit, dropping it down. There are 6.02 times 10 to the 23rd molecules. and we have the unit that the problem is asking for. So now this simply becomes a standard dimensional analysis T-chart problem. You're going to multiply everything on the top together. So 50.03 times 1 times 6.02 times 10 to the 23rd. Get an answer. Divide that by the stuff on the bottom. So divide that by 64.1. And when you do that, and make sure you're getting the same value that I am getting, you get 4.72 times 10 to the 23rd molecules. If your exponent on the 10 there disagrees with mine, then, but the value is the same, 4.72, it means that you're probably doing something wrong with punching the numbers into your calculator, and we can go over that together. Next up, what is the mass of 12.3 liters of fluorine gas at STP? So the problem gives us volume of a gas at STP, and it's asking for mass. We do not have a direct conversion, so we are going to convert volume to moles and then moles to mass. Notice how we're going through the mole conversions. We're taking one unit, turning into the mole, turning the mole then into something else. The mole is the comparative unit in chemistry. We cannot directly compare volume to mass. We can, however, go through the mole. So we're going to start with the number the problem gives us, 12.3 liters of a gas at STP. Take the unit, drop it down, bottom right, because we want it to cancel. We're going to turn liters into moles. So what's the relationship there? 22.4 liters of 1 mole of a gas at STP. Great. We've taken care, essentially, of this step. That's what that first bit is. But we don't have the answer. We don't have mass. So we're going to extend our T-chart. Next part of the conversion, going from moles to mass. How do we go from moles to mass? That's GFM, gram formula mass. Liters have canceled, so 1 mole. Again, Mrs. Julian being tricky. Fluorine gas right here. If you're plugging in 19, because you go to your periodic table and you say fluorine, fluorine has an atomic weight of 19. I'm tricking you. Mrs. Julian is a trickster. She is laying traps deliberately to see if you will fall into them. Diatomic. Fluorine gas. Fluorine gas is F2. It is not 19. No, it is 38. 19 times 2, 38 grams. I will get you every time with this until you figure out. Remember, Haber-Finkel, HOBR-FINNCL, the diatomics, 38 grams per mole, F2 gas. Moles cancel, and then again, go through, do the math. 12.3 times 38, multiply all the top numbers together, divided by the bottom numbers, 22.4 liters, and we get an answer of 20.9 grams. 20.9 grams. Next up, what is the volume of 4.45 times 10 to the 24th atoms of xenon gas at STP? Okay, so once again, just sort of pointing out, we do have, it's asking about a volume of the gas at STP. The number we're starting with is, the value we're starting with is atoms. So we're going to take that atoms, we're going to turn it into moles because we do not have a direct conversion for atoms to volume. So we're going to have to go through the mole in the middle. Once we get moles, we can turn that into volume. Standard T-chart problem. These are all dimensional analysis problems. 4.45 times 10 to the 24th atoms. Take the value, drop it down, take atoms, put it there. We want to turn, first step, atoms into moles, so moles go on top. What's the conversion factor here? For every 1 mole, there's 6.02 times 10 to the 23rd of whatever particle it is you're looking at. In this case, we're looking at atoms. That's 6.02 times 10 to the 23rd. That takes care of that particular step. That's Avogadro's number right there. But we don't have volume. The problem is asking us for volume, so we're going to extend our T-chart. We're going to take the mole that's on top here. We're going to drop it down to the bottom. It's asking for volume. We can do that, so we can do liters. Plug in the numbers. For every 1 mole, there is 22.4 liters of the gas. So moles cancel. Atoms had already canceled out. And again, you're going through and you're doing that math. Now, here's where you do need to be careful, especially with the 6.02 times 10 to the 23rd being on the bottom. Careful with how you're plugging it into your calculator. The answer is 166 liters. If you got 1.6, 1.66, something like that, but you don't have the same exponent, you've got like a really large exponent, like 10 to the 45th, 47th or so, means you're plugging the numbers incorrectly into your calculator. Come see me and we'll make sure you're squared away on that. And you might have gotten something a little bit different, but I am looking at sig figs here. When I go through and I do this math, 166, 3 sig figs. This value right here, 3 sig figs in it, so I'm keeping it to 3 sig figs. So that is the mole conversion review. Just taking you through some sample problems, reminding you what you can do with mole conversions, and essentially the standard mole map stuff.